Thank you, Orion, for the introduction. So I'm going to be talking today about my research that I just wrapped up on Atlantic stingrays. Some of you may have seen them in the aquarium room. And so I was looking at the impacts of salinity changes on their critical oxygen limits as an estuarine species. So Bostoni did a lot of the heavy lifting for me already today, if some of you are here for her talk. So this may be a refresher for you. But estuaries are characterized by the input of both freshwater and saltwater mixing in an environment. That amount of salinity can change based on a seasonal or a daily basis, based on tidal influx, precipitation. But we know estuaries experience a lot of other environmental changes as well on that same timescale, including temperature and dissolved oxygen. And so if you're an organism living in this environment, you're going to have to deal with a lot of those fluctuations pretty regularly. But we know that these organisms are capable of dealing with these changes. And one of the ways we know that is by looking at their metabolic rate. So this is quite a famous graph in our lab. Again, you will have seen it before, but I'm just going to briefly go over this for those who need a refresher. But metabolic rate is dependent on the amount of available oxygen to a given point. And that is our metabolic curve here. Up at the top, that's our plateau where we reach our maximum metabolic rate. This encapsulates everything from reproduction, growth, as well as prey capture and predator avoidance. So those energetic events where you really need to push to your top metabolic rate. And associated with this maximum metabolic rate, we have our critical oxygen limit, our p-crit max, which is the critical partial pressure of oxygen that's required to meet this maximum metabolic rate. And any amount of oxygen below this point, metabolic rate is going to be dependent on that amount of oxygen. And that relationship can be shown with the oxygen supply capacity, or alpha value, which, as Bostoni mentioned, is the ability or the capacity for an organism to supply oxygen to its tissues. So when I look at these three values, I'm really interested in that p-crit max value here, because that dictates pretty much how well an organism is going to deal with low oxygen. And that p-crit max value actually changes dependent on the species. And we can see that those species can be classified by the habitats that they're typically found in. For example, in marine environments, shallow water marine environments, we see that their p-crit max value is right around 21 kilopascals, which is pretty much 100% air saturation. That's that top layer of water that's really well mixed. It's getting a lot of dissolved oxygen to it. And so those organisms that live in these habitats need full air saturation in order to reach their maximum metabolic rate. Fortunately for them, that doesn't typically tend to be an issue, because we do see a lot of really good mixing in these shallow water marine environments. But as previously talked about, estuaries, they do see a lot more fluctuations. So when we look at estuarine species, we see that their p-crit max is actually about at half of what marine species are, right around 12 kilopascals. There is some variation with that depending on the species, but we can tell that their maximum metabolic rate can be reached at half the amount of available oxygen than shallow water marine species. We also know that metabolic rate can be temperature dependent or dependent on other variables as well. So for example, with temperature, we typically see an overall increase in maximum metabolic rate along with a temperature increase, which can often result in an increase of that oxygen supply capacity, which was what Bostoni's research was showing. And you can see generally as temperature increases, in this example with the killifish, you can see that their maximum metabolic rate or their routine metabolic rate, which is RMR, generally increases with temperature. But I want to know, how does salinity impact this metabolic curve? It's something we don't quite understand as well. We know, obviously, salinity can change the amount of hemoglobin binding within blood plasma, but we don't know exactly where this curve is going to be affected when we change the salinity with estuarine species. We know that these species experience a lot of habitat shift, or it's not habitat shift, environmental shift in these abiotic factors. And we know that they can tolerate both low salinity, high salinity, and hypoxic conditions. But how exactly are we going to see these metrics change? And when I look at these, I'm most interested again in these three variables. So I'm going to be studying maximum metabolic rate, the oxygen supply capacity, and the pCrit max. And to answer these questions, I will be using the Atlantic stingray, an allegedly very abundant species in the area, according to FWC. I don't know, but they're pretty common around here. They're also called the common stingray as well. And they're typically found in less than 1 meter of water around the Gulf of Mexico and up the temperate east coast of the US. They're found everywhere from fully marine environments to freshwater conditions. There's a permanent population in the St. Johns River. And we see populations that move habitats and shift habitats in and out all the time. So they're a really great study species to be using for this to test how salinity changes are going to impact those factors. So I tested 18 stingrays total across 3 salinities. For those of you who can do quick math, that's 6 stingrays per salinity treatment. And first, when I was looking at maximum metabolic rate, I decided to measure this variable at 3 different oxygen saturation percents. First at 100%, which is again around 21 kilopascals, and then again at 130, so a hypersaturation. And that's really to determine where that plateau is for that maximum metabolic rate. And then I also tested their maximum metabolic rate at 60% air saturation, or around 12 kilopascals. The reason I was looking at this is because I wanted to know, are we going to see them respond like marine species or shallow water marine species with a higher pCrit max, or is it going to be more like Estuarine species and have a pCrit max around half of that value? Or is that going to depend on the salinity that they're in? I also measured oxygen supply capacity using hypoxia trials, which is essentially when I put a stingray in a closed box and I allowed them to breathe down the oxygen almost until they were about to die, and then I pulled them out and they were fine and no stingrays died in the hypoxia trials. Everyone was released just fine. And using these 2 metrics, I was able to use trusty y equals mx and calculate that PC max. So the stingrays that I used were collected from Lassing Park and Weeden Island primarily, or Riviera Bay. They were collected and brought back to our aquarium room where they were allowed to be in the tanks. They were fed regularly on public shrimp, and they loved this free food falling from the sky. And they were worked up, and then right before their salinity treatments or their trials, they were acclimated for 24 hours before each trial. So unfortunately, stingrays don't speak very good English. So when I asked them to swim as fast as possible, they weren't really understanding me. So I had to do what we usually do in respirometry, which is to induce them into what is hopefully their maximum metabolic rate. And that involved me chasing them with a long PVC pole until they no longer responded to me poking them. And then when that happened, I flipped them over like pancakes. And then they would flip themselves back over and I'd flip them over again. And when they were too tired to right themselves, I removed them from the tank, left them for 1 minute of air exposure, and then put them into the respirometry chamber here. And this was already acclimated to the right salinity and temperature and whatever oxygen percent I was testing at, and the amount of oxygen within the chamber was measured during this period. Then, of course, once the stingrays were done with all of their metrics, they were released back where they were captured, full bellies filled with public shrimp, happy to see me go, and I was very happy to be releasing them as well. So they had very happy send-offs. Some of the interesting findings was that actually oxygen supply capacity increased as salinity decreased. And it was significantly different between the low salinity groups and the full salinity groups. And what's interesting is you can see that there is a gradual increase in oxygen supply capacity. So that half salinity group is right in between those. Another interesting finding was actually maximum metabolic rate decreased with salinity. So at a full salinity, the stingrays were able to achieve a much higher maximum metabolic rate than they were able to at a half or a low salinity. So they weren't able to reach that same height or maximum metabolic rate in these low saline conditions. And putting these 2 variables together, we were able to estimate our pCrit max. And it was significantly lower in the low salinity groups. it was actually more in line with what we see with freshwater species. And at a full salinity, we see a peak crit max right around, I think it's around 15 or 14, which is pretty much in line with what we see with estuarine species. So even in full salinities, they're going to behave like estuarine species, but as salinity is decreasing, they're actually getting more, they're better at supplying oxygen to their tissues because of that increasing oxygen supply capacity. So if I were to put this onto that famous graph that you saw at the beginning, it looks something like this. And you can see that as you go, as salinity decreases, there really is that increase in slope for oxygen supply capacity. And you can very clearly tell that that metabolic rate is not plateauing at quite as high of a point as salinity decreases. There was a small increase in maximum metabolic rate with the hypersalinity. It is somewhat observable here, but it wasn't statistically significant. But it isn't uncommon for estuaries to see hyperoxygenated conditions. So why are we seeing these low maximum metabolic rates and low salinities? Well, contrary to this photo, there's actually not very many predators that stingrays see in estuarine or freshwater habitats, aside from the occasional alligator or occasional bull shark as well. There's much more predators, many more predators in marine environments. And this may be because when they're in these low estuarine conditions, they haven't evolved the ability to have as high maximum metabolic rates because they haven't needed to. Estuaries are famous for using them as nursery grounds and habitats because they're protecting species because of the fewer large predators. Another possibility is that it might be the cost of osmoregulation. Elasmobranchs osmoregulate differently than teleosts do because they primarily use urea and TMAO in order to osmoregulate. And when they're in low salinities, they're pretty much excreting urea constantly. So that may be one of the impacts there. Another possibility is that I was looking at acute acclimation times to these salinities. 24 hours is a short period of time. We have seen studies that show that maximum metabolic rate will actually typically increases when salinity changes, but occasionally, we do see changes in maximum metabolic rate when salinity is changed within 24 hours, and it does typically return to normal after a week. However, it is still ecologically relevant because, like I said, in estuaries, you are seeing conditions change in salinity on a daily basis, either because of tidal input, precipitation, or because they're relocating their habitats. Overall, though, these guys are pretty hardy. Trust me, they're very hardy. And I'm not too concerned about them, especially in the face of increasing fluctuations in estuaries because of climate change conditions. They're pretty well equipped to deal with these drastic changes. I want to say thank you to my advisor, Dr. Brad Seibel, as well as my advisor in Australia, Dr. Jody Rimmer, my USF lab mates, Alec in particular for the help with data analysis, and my intern Maria, who's here today. She was out there collecting stingrays with me every single day, even when I didn't want to, and especially when the stingrays didn't want us to. So thank you to both of them. And are there any questions?